Welcome to Physics with Joe. Today we're going to be looking at the photoelectric effect, which was the first real proof that light can behave like a particle called a photon, and for which Einstein's explanation of the photoelectric effect would eventually win him the Nobel Prize in Physics. First, I'll talk about what exactly the photoelectric effect is. Then we'll look at some of the features of the photoelectric effect that could not be explained by the classical wave model of light. Then we'll look at some of the postulates that Einstein used in his explanation of the photoelectric effect. And then finally, we'll look at what the photoelectric effect equation says and how to use that in solving problems dealing with the photoelectric effect. So without further ado, let's jump right into it. The photoelectric effect is the phenomenon in which light shining on a metal can cause electrons to be ejected from the surface of the metal if the light has enough energy. Basically, the light has to have a minimum amount of energy above what's called the work function of the metal, which is the minimum amount of energy required to eject an electron from the surface of the metal. The work function depends upon the type of metal and how tightly bound the electrons are. If light shining on a metal does not have enough energy, if the energy is less than the work function of the metal, no electrons will be ejected no matter how intense the light source is. If light shining on the metal has more energy than the work function of the metal, then that excess energy can go into the kinetic energy of the ejected electrons. So let's take a look at the photoelectric effect in action. What this animation is showing is a light source whose intensity and wavelength I can vary shining down on a metal. In this case, the metal is zinc. Zinc has a work function of 4.3 electron volts. I'm going to get to that in a little bit, what exactly an electron volt is. But because of the work function of zinc, the maximum wavelength that will cause electrons to be ejected from the zinc is 288 nanometers. We call that the threshold wavelength. Any wavelengths above 288 nanometers, then the light does not have enough energy to eject electrons. Any wavelengths below 288 nanometers, then the light does have sufficient energy to cause electrons to be ejected. So if the, let's say, wavelength of the light is 300 nanometers, that light does not have enough energy to cause electrons to be ejected from the zinc surface. It does not matter how intense the light is. If the energy of the light does not have enough energy to overcome the work function of the metal, it doesn't matter how intense the light source is. So 288 nanometers for zinc is the threshold wavelength. And that light has enough energy to cause electrons to be ejected. At 288 nanometers, the light has just enough energy to eject electrons from the surface of the zinc. If I increase the energy of the light by decreasing the wavelength, now the light has more than enough energy to eject electrons, and the excess energy above the work function can go into the kinetic energy of the ejected electrons. So as I increase the energy of the light, the electrons are ejected with more kinetic energy. And increasing the intensity does not result in more kinetic energy, it just results in more ejected electrons. In the classical model of light, light is treated like an electromagnetic wave, and the intensity and the energy of the electromagnetic wave depends upon the amplitude of the wave, not the wavelength or frequency. And several of the features of the photoelectric effect that we see from experiment are inconsistent with the wave model of light. Feature number one is that the maximum kinetic energy of the ejected electrons is independent of intensity and increases with increasing frequency. Now, the classical model of light predicts that if I increase the intensity of the light will have more energy, resulting in the electrons being ejected with greater kinetic energy. And that's not what we see. If I increase the intensity of the light, I have more electrons being ejected from the surface of the metal, but I do not increase the maximum kinetic energy of the ejected electrons. And also, classically, the kinetic energy of the ejected electrons should not depend upon the frequency or wavelength of the light, only the intensity. And again, that's not what we see. If I decrease the wavelength or increase the frequency of the light, the electrons are ejected with more kinetic energy, which is not consistent with the classical model. A second feature of the photoelectric effect that's not consistent with the classical wave model of light is that even at low light intensities, electrons are ejected almost immediately, after about 10 to the minus 9 seconds, a nanosecond. Classically, at very low light intensities, it should take time for the electron to absorb enough energy to break free from the metal, and that's not what we see. As soon as the light hits the metal surface, if it has enough energy, the electrons are ejected almost instantaneously. The third feature of the photoelectric effect that is inconsistent with the wave model of light is that no electrons will be ejected if the frequency of the light is below a certain threshold frequency that depends upon the kind of metal. So if the frequency is not great enough, then no matter how intense the light source, no electrons will be ejected. Classically, it should not matter what the frequency of light is, as long as the light is intense enough, then the electron can gain enough energy to break free from the metal, and that's not what we see. In developing his explanation for the photoelectric effect, Einstein used three postulates or assumptions. The first postulate is that rather than being an electromagnetic wave, light of frequency f consists of discrete quanta called photons. Each photon travels at the speed of light and has energy E equals hf, where h is Planck's constant and f is the frequency of light. The second postulate that Einstein made was that photons are emitted or absorbed on an all or nothing basis, meaning an object can emit a photon or two photons or three photons, but it cannot emit a portion of a photon. Similarly, when an object absorbs a photon, it has to absorb an entire photon. You cannot absorb a portion of a photon or half a photon. And then the third postulate is that when a photon is absorbed by a metal, it delivers all of its energy to a single electron. Using those postulates, Einstein developed his explanation for the photoelectric effect, and let's take a look at what the photoelectric equation states. The photoelectric equation developed by Einstein is a relatively simple equation, and it states the following. K max, which is the maximum kinetic energy of the ejected electrons, equals hf, which is the energy of the absorbed photon, where h is Planck's constant and f is the frequency of the light, minus E naught, which is the work function of the metal, which again is the minimum amount of energy required to eject an electron. And this equation is really just based on conservation of energy. If an electron absorbs more energy from a photon than is required to eject the electron, then that excess energy absorbed by the electron goes into the kinetic energy of the electron. The reason we use K max, the maximum kinetic energy, is because the electron can lose energy in the process of escaping the metal. So again, K max, the maximum kinetic energy of the ejected electron, is equal to hf, the energy of the absorbed photon, minus E naught, the work function of the metal. So let's take a look at each of these three quantities and how you go about using them in solving problems involving the photoelectric effect. Let's start by looking at the equation for the energy of a photon, E equals hf. In this equation, h is Planck's constant, f is the frequency of light in hertz. And the value that we're going to use for Planck's constant is going to depend upon the units that we use. H is either equal to 6.63 times 10 to the minus 34 joules seconds, or H equals 4.14 times 10 to the minus 15 electron volt seconds. And an electron volt is just a common unit of energy that we use often when dealing with particle physics. And an electron volt is equal to 1.602 times 10 to the minus 19 joules. And usually when dealing with a photoelectric effect, we're going to be working in units of electron volts. So the value that we're going to use for Planck's constant is 4.14 times 10 to the minus 15 electron volt seconds. And just as a quick aside, an electron volt is defined as the energy an electron gains when being accelerated through a potential difference of 1 volt. That's not really important for our purposes. Just keep in mind that an electron volt is a small unit of energy that we use when dealing with particle physics, and it equals 1.602 times 10 to the minus 19 joules. Now, because for any light wave or photon, wavelength times frequency equals the speed of light c, we can solve for frequency and show that frequency equals c divided by lambda, the speed of light divided by the wavelength. Using that, we can substitute in for frequency c over lambda, and a second form for the equation for the energy of a photon, rather than E equals hf, can be E equals hc divided by lambda. And this is often useful when we're giving the wavelength of the photon and not the frequency of a photon. Now, because this quantity hc comes up so often, there's a very useful shortcut you can use, and that shortcut is that the value of hc is equal to 1240 electron volt nanometers. Let's take a quick look at where that comes from. Using Planck's constant as h equals 4.14 times 10 to the minus 15 electron volt seconds, if I take h and multiply by c, where c is the speed of light, 3 times 10 to the 8 meters per second, and then I convert to nanometers, where a nanometer is 10 to the minus 9 meters, h times c ends up being equal to 1240 electron volt nanometers. So when using the equation for the energy of a photon, E equals hc divided by lambda, if I express lambda in nanometers, so the wavelength in nanometers, then the easiest way to get the energy of a photon is E equals 1240 electron volt nanometers divided by the wavelength in nanometers. And that will give you the photon energy in electron volts. The work energy E naught is the minimum energy required to eject an electron from the surface of the metal. And the work function depends upon the type of metal and how tightly the electrons are bound. Now, the work function E naught can be shown to be equal to Planck's constant times F naught, where F naught is called the threshold frequency and is the minimum frequency that will cause electrons to be ejected from the surface of the metal. Now, using, again, the frequency equals c divided by lambda, the speed of light divided by the wavelength, a second equation we have for the work function is E naught equals hc divided by lambda naught, where lambda naught is the threshold wavelength, and that is the maximum wavelength photon that will cause electrons to be ejected from the surface of the metal. So we can always figure out the work function if we're given either the threshold frequency or the threshold wavelength. Finally, let's take a look at Ke max, the maximum kinetic energy of the ejected electrons. Now, usually when running a photoelectric effect experiment, we've got the metal that's being illuminated inside a vacuum chamber. And oftentimes we'll set up two plates, a positive and negative plate, and apply a potential difference between the plates. And the stopping potential is the potential difference required to prevent all electrons from reaching the negative plate. So in this case, if I have a potential difference of negative 2.90 volts, that will prevent all electrons from reaching the negative plate. So we therefore say that the stopping potential is 2.90 volts. We usually just take the absolute value and drop the minus sign. So if I apply a potential difference of 2.90 volts between these two plates, none of the electrons will reach the negative plate. And there's a nice shortcut in that the maximum kinetic energy of the ejected electrons is related to the stopping potential required to prevent all electrons from reaching the negative plate. And let's take a quick look at that shortcut. The equation that relates K max, the maximum kinetic energy of the ejected electrons, to the stopping potential is K max equals E times V stop, where again, K max is the maximum kinetic energy of the ejected electrons, E is the magnitude of the charge on an electron, 1.602 times 10 to the minus 19 coulombs, and V stop is the stopping potential. And the useful shortcut you can use is that if the stopping potential is expressed in volts, then kinetic energy max, K max, will be in electron volts. You don't even need to do the conversions or anything like that. Just realize that if V stop is in volts, K max is in electron volts. So for example, if you know the stopping potential is 1.2 volts, then you automatically know the maximum kinetic energy of the ejected electrons is 1.2 electron volts. So putting it all together and summarizing, the simple equation for the photoelectric effect is Kmax equals HF minus E naught, where Kmax is the maximum kinetic energy of the ejected electrons, HF is the energy of the absorbed photon. Again, we could also write that as hc divided by lambda, and E naught is the work function of the metal, which is the minimum amount of energy required to eject an electron from the metal. Now the work function E naught is equal to Planck's constant h times F naught, where F naught is called the threshold frequency, which is the minimum frequency photon that will eject an electron. Work function is also equal to hc divided by lambda naught, where lambda naught is the threshold wavelength, which is the maximum wavelength photon that will eject an electron. And remember, a useful shortcut is hc equals 1240 electron volt nanometers. And then finally, Kmax is related to the stopping potential through the equation Kmax equals E times V stop, where E is the magnitude of the charge on an electron and V stop is the stopping potential. And the nice simple shortcut is that if the stopping potential is expressed in volts, then the kinetic energy max is in electron volts. Well, that is it for today's episode of Physics with Joe. Thank you so much for joining me, and until next time, happy physicsing. Happy physicsing.